Hello, this is Mr. Messerman's podcast for Chemistry of Earth number 5. I can build models of ionic crystals of any empirical formula. To do so, we will figure out, using the periodic table, first, the outer shell electrons on the atoms that you're going to be building into a crystal. Then the electrical charge of the ions that form from those atoms. Then the empirical formula of the crystal itself. Alright, let's start with sodium chloride, a good old favorite. And I've drawn sodium and chlorine with their electron shells here. How do we know how many electron shells? Well, they're both in row 3. Here's sodium, and way over here is chlorine. Row 3, 3 shells. Now, all we care about is their outer shell, because that's the one that does the bonding. So, how do we know how many are in the outer shell? Well, that is the column number. For sodium, it's 1A, so we'll just put 1 dot. For chlorine, it's 7A. So we'll put 7 dots, and as usual I pair them up, not that it matters too much. And we'll put that one right there. Okay, so here's sodium and chlorine with the outer shell electrons. Okay, the next step is to figure out the charge on the ions. Charge on the ions. Well, do a quick run through of the rule on this. The rule for ions, the rule for atoms really, is that they want to become stable. And to become stable is to become like a noble gas. So, here's sodium again. Now, sodium could become like argon by gaining 7 electrons, so that it would have 18. That's way, way, way too difficult. There's a lot easier path. That path is just to go right around here and become like neon, which is 1 lower than sodium. So how does it do that? It gives away this single electron. Chlorine, on the other hand, wants to become like argon because it's right next door to argon. It's much easier for chlorine to gain 1 than to lose 7, so it gains 1. And that makes it like argon, which is very stable. So where is it going to gain it? Well, it's going to gain it right here. It's going to put another one right in the outer shell. So look what happens. When sodium and chlorine get together, what would happen if you put sodium metal with chlorine gas, for example, is the sodium would actually give this electron to the chlorine. Okay? And there would be a violent reaction if that happened. Now, the sodium and chlorine on Earth right now has already done that, and so we don't see this violent reaction going on all over the place. The chlorine has already gotten 1 electron, and let's make it red here. So the chlorine would look like this. And the sodium has lost this electron. Just erase all this here. And the sodium would look like this with no outer shell electrons. Chlorine would have 8, sodium would have none on the outer shell. But now its outer shell would be in here, and it would have 8 on the inside. And that is nice and stable. Well, since sodium gave up 1 electron, you've subtracted a negative charge, and the charge on the sodium is 1 positive. Chlorine has gained an electron, and you've added a negative charge, so the chlorine becomes a 1 minus ion. Okay? Subtracting an electron here subtracts a negative, that's a positive. Adding an electron here adds a negative, and that becomes a negative. Okay, so we've determined that we have sodium with a 1 plus charge, or just plus. We have chlorine. It's 1 minus charge. We can just write minus. Those are our ions. Those are the charges on our ions. Final step, determine the empirical formula of sodium chloride. Well, this is a pretty simple one, folks. And the rule is that you have to balance the charge. When two ions get together, the charge will always end up being 0. You have to balance the charge. So it's very easy to balance plus and minus. All you need is one of each. And so the formula becomes NaCl, sodium chloride. The charges cancel and you don't write them in the formula. We just write NaCl. It's pretty simple. One of each, and you've canceled the two charges. And that's the force, the electromagnetic force that holds sodium and chlorine together. Okay? I'll do another example in a minute when they're not 1 and 1. Now this is called an empirical formula because it is reduced. It equals a reduced formula. The simplest, lowest formula there is. It's like a least common denominator. Okay, we've reduced it down to the basic ratio of the ions. Okay. Now, why is this important? Well, it's important because there really is no such thing as an NaCl, 1 sodium and 1 chlorine. Okay, NaCl is a salt. It happens to be table salt, but a salt equals an ionic compound. Alright? Anytime you're working with ions that get together, you have a salt. It could be sodium chloride, or sodium oxide, or sodium sulfide, or calcium oxide, or calcium chloride. They're all salts. Okay? Ionic compounds that also create crystals. Okay? And a crystal is made up of billions and billions of sodium and chloride ions. Okay? And they look something like this. Sodium and chlorine bonded with its ionic bond. But it doesn't stop there. We can't just stop with 1 sodium and 1 chlorine. They are connected in this cubic fashion like this. Write them out here and then fill in some of the bonds between them like this. Now it doesn't stop there either. I would keep going to sodium and chloride and sodium and chloride. This is where I need to speed this up a little bit. And then it would go off in 3 dimensions. So, oops, we'd have sodium and chloride connecting in 3 dimensions. And we get this 3-dimensional grid that looks something like this. Maybe you're getting the picture here, but I would continue to build this out in 3 dimensions until I had a crystal that perhaps had a shape like this. Okay. Oops. Did something wrong here on my crystal. There we go. That's all right. So sodium chloride crystals are large blocks of sodium and chlorine that form a three-dimensional cubic pattern, such as this. And so the empirical formula is just the reduced formula from Na billion Cl billion down to NaCl. A much better illustration of sodium and chlorine. Chlorine ions are actually much bigger than sodium. Here's the sodium. And there's the chlorine. A nice, tight, three-dimensional grid pattern. That is the crystal. Now, what about this strange-looking crystal? What I see is a few purple in the middle, but they're surrounded by all these red. And if you count them up, you'll see there are twice as many red as purple. So it makes the crystal look a little different. Well, this is sodium oxide. Basically, sodium and oxygen become ionized to form sodium plus and oxygen 2 minus, because the oxygen needs to get 2 more electrons to become an ion, a stable ion. It's in column 6 on the periodic table, so it has 6 and it requires 2 more, which you can get from sodium or anywhere else. So oxygen ends up with a 2 minus charge, sodium with a 1 plus, and the empirical formula down here is sodium 2 oxygen 1, or Na2O. Na2O. There are 6 purple in here if you count them, and there are 12 oxygens in this little unit of a crystal. Again, continue this crystal out in 3 dimensions and you'd have sodium oxide. Thanks for watching.